Saxon's Calculus, Lesson 85, is applications of the definite integral, or in parentheses, work, for the second time we're discussing it. So example 1 says a rectangular tank is 6 meters high, 10 meters long, and 4 meters wide. If the tank is full of water, find the work required to pump the water out of the tank. So we know that we still have our 9,800 from our earlier lesson, and we will be integrating. And the area of the bottom of this is 4 by 10. So that's giving me another constant of 40 that I'm going to put out here. And then what I'm dealing with in the change is the fact that it's 6 minusing the y as it's dropping out. And that will need to go from 0 to 6. So they're giving me here that this is 392,000. I'm not doing that in my head. And then when I integrate here, I'm going to be getting 6y minus 1/2 y squared, and plugging in the 0 and the 6. The 0 will not be necessary. The 6, calculator, half of 36, 36 minus that would be that same half multiplied by 392. So I'm just going to look, and they're going to tell me that it is 7,056,000, and then joules answers that question. Okay, example 2. All right, so when I started to draw it, I realized that I drew it instinctively without looking at the fact that they called it a trough. So this is upside down. It should be this actually on the bottom, but the rest of the dimensions are fine. So we have a triangular tank shown is filled with oil to a depth of 2 meters. The dimensions of the tank are all in meters. Find the work done in pumping the oil out of the tank if the weight density of the oil is 5,000 newtons per cubic meter. All right, so then what I did was I said, okay, I actually am having a triangle here that is this 5 and half of this. So that's only 3 here. So if I Pythagorean theorem, that gives me 25 minus 9, which is 16. Square root of 16 is 4. So since this is actually 4, then in my equation with the 5,000 as the constant, and again, picture that flipped upside down. So it's this number here is the 4. It's the 4 draining out, so it's 4 minus y. Now, I didn't write the rest of the equation in because, as you recall from the last example that we did, to get that, I had to find the rise over the run. Well, if I do that here with this triangle, it's rising 4, running 3. So we're going to get y equals 4/3 x. I'll write that over here. Y equals 4/3 x. Now, actually, before I turn the page, they do make a clarification that we are using mathematics to solve a physical problem. There's no way to do it. The tank is symmetrical, so they decided to find the work required to pump the oil out of half the tank, which is why I did half here, and then double our answer at the end. So at the moment, this is, so just remember we still have to deal with that doubling. All right, so we've got our 4 minus y, and then we need to do our, and again, I need to have the other variable in here. So this is going to flip and become 3/4 y, so that they match now. So I had to solve for the x here. Then distribute. So that 4 cancels and leaves me 3y minus 3/4 y squared. And then integrate from 0 to 2, and I'm getting that from the fact that it said in the original it was 2 meters deep. But because I'm dealing with volume, I also needed to multiply by height. So this 20 as the height is out here multiplying with the other constant of 5,000. So we've got then 100,000, 1, 2, 3, 4, no, 10. Where did my other z? Did I? 20, yes. 1, 2, 3, 4 zeros. I don't know where they got. Let me ponder on where that came from. All right, so then we are dealing with this becoming y squared. So 3 halves y squared minus, add to a 3. The other 3, that's going to cancel with that 3 and leave me with, goodness, y cubed over 4. Mercy. Plugging in the 0 to 2. Zeros plugged in are going to kill those off. 2's plugged in with the calculator is going to give me, I'm going to pause it while I find that 0. Duh, 5 times 10. 5 times 2 is 10. There's the extra 0. This is correct. So once I've done the calculator work with plugging the 2 into this, you should end up with that multiplying with your 100,000 and the doubling of that. So that should give you 400,000. Yes. And then you're doubling that so that your final answer is 800,000 joules. And now example 3. End of a tank is a semicircle whose diameter is 20. Bad time to cough. Okay, so okay, let's now read example 3. The end of the tank is a semicircle whose diameter is 20 meters. So I labeled the radius at 10. Tank is filled to a depth of 4 meters with a fluid whose weight density is 6,000 newtons per cubic meter. Set up an integral, so we're not solving it, that could be evaluated to find the work required to pump the fluid to a point 20 meters above the top of the tank. So I know that I'm dealing with a circle, which is pi times radius squared. And since the radius was 10, we're dealing with 100. So if I'm solving for just a piece of it, then that is 100 minus the y squared, the square root of that. Let me clarify. I was doing the equation of the circle, and what I wrote was the area of a circle, and that's not what I meant. So the equation of the circle is x squared plus y squared equals the radius squared. There's my 100. And then I'm solving for the x squared. So I'm getting the 100 minus the y squared square rooted to make it x equals. And then I need to figure out, and it said it wanted it to, 20 meters above the top of the tank. So I know that I'm multiplying this with the 20 minus the y for that adjustment, and then the dy at the end. And my numbers for integration are a little bit unique because I'm dealing with going from a radius of 10 and this one, which is at 4, and I'm bringing it up to here. So I'm working it backwards. I'm actually negating it. So I'm going from, and then the 10 minus 4 is the gap of 6. So I'm actually going from -10 at the top to -6, being the difference between the 10 and the 4. I also needed to take into account and I didn't label it on here, this was 40. So I need to multiply for volume with that height, so that puts an extra 40 out here with my constant. Now, since they don't want me to solve it, I should just need to summarize it. And again, they're going to put their constants after or inside the integration. I would keep it outside. So there's that number, this one multiplying with this one, and they don't want me to solve it out. The only other thing is, again, we are doubling this because we were only dealing with a part of the tank. And that's not instinctive. You just have to kind of think your way through. In the picture, what am I doing? I'm dealing with this part of it only, not the whole thing.